So today's going to be an unusual introduction because the person in our department who actually knows Anne the best, the person in our department who knows Anne the best is Neil Weiner. Unfortunately, he couldn't be here today, but he's given us a video intro for Anne. Just before he came to NYU, Neil was Anne's postdoc in Seattle. So.
It's my great pleasure to welcome to NYU today Anne Nelson. Anne Nelson got her PhD from Harvard and was a junior fellow, music society fellow at Harvard after that. She began her faculty appointments at Stanford University before moving to the University of California, San Diego, and finally to the University of Washington, where she was physics and since 1994, and is duly awarded. She has received a Guggenheim Fellowship. She's a member of the American Academy of Sciences and National Academy of Sciences. More impressive than any awards for Anne, though, is the degree which she has been impactful on a tremendous range of subjects in Harvard. To do this, and I just pulled up her citation list on Inspire, of course, it's too long to try to do it anything. So I limited myself to just what Inspire calls famous papers based on their citations. And just limiting myself to those, Anne has had tremendous impacts on formal properties of supersymmetric theory, Higgs physics, baryogenesis, or the question of why the universe is made out of matter instead of antimatter, black holes, nuclear matter, the phenomenal oscillating impacts of supersymmetry, so the signal of the LHC, neutrinos, tests of gravity, dark energy, and CP violation. And if I were to move to her more obscure papers with only 1 to 200 citations and her topics we cover, of course, what's impressive is not measured in citations, and what's really impressive and to me is the degree to which she's really willing to tackle any problem out there and is excited to find something new that she can apply herself to, even one requiring to invest a lot of time and energy in learning new things. And in fact, that's actually a positive thing for her. It was my great privilege to be able to work with her from 2000 to 2004 on a few of these topics, and it is also my privilege to welcome her to NYU. So, Anne, we look forward to hearing from you today.
Well, thanks, Neil.
Thanks, Neil. I was afraid he was going to show a photo of me in Santa Barbara drinking wine from the bottle. The last time he introduced me, he did that. Okay. No, that's okay. Nice introduction. Thank you. So thank you for inviting me. How is this volume?
Good.
Okay, got this microphone over here. So, all right, sort of a slightly cute title. So natural has an English definition of existing or caused in nature that is not made or caused by humankind. So, I mean, how could the LHC possibly even address such a question of whether the physics at the energy scales it can explore is natural? Well, so obviously I will later in this talk get to a much more limited definition of natural, which the LHC can address. But let me just start by introducing the LHC itself, the Large Hadron Collider, because I know this is a broad audience, and some people even started physics after the LHC is running, which is mind-boggling to me because this is, to me, still a fairly new and exotic machine. So the Large Hadron Collider was built in the old electron-positron tunnel in Geneva. It's 17 miles in circumference, and you can see, you don't actually see those circles. I think those are drawn from the air, but a series of accelerators, smaller circles that inject into larger, and then finally into the big deal. And what it injects into those tunnels is protons, which are a type of hadron. So the LHC itself you can't see on the surface like that. It's underground. And I'm going to be focusing on the two general purpose experiments, ATLAS and CMS. And this picture shows also, two other interesting experiments, which I'm not so much going to focus on in this talk. There are also some, I think officially there's some smaller experiments as well, a total of 7 different experiments. So if you actually were to go into the tunnel, which you can't do anymore right now, but one time you could, what you would see is a bunch of superconducting magnets, or the outsides of them. And so these magnets produce magnetic fields to bend the protons in circular orbit, and they also have electromagnetic fields which accelerate the protons to almost the speed of light.
What's gamma?
Do I say what gamma is? Oh, what is gamma? So gamma is the ratio of the energy of the beam to the proton mass. The proton mass is about 1 GeV, and the energy of each beam is currently 6.5 TeV, 6.5 trillion. So gamma is 6,500. So that's big. Okay. So the two experiments that I'm going to be mostly focusing on results from, so there's the ATLAS, which has this really, I think kind of a weak acronym, because toroidal LHC apparatus, but it's a nice name, and it's the one that the local LHC group here is in, also the one from my institution. And since I got this picture from my institution, it points out that they built these things. This gives you the scale of the thing. It's actually enormous. Let me show you some fun facts. So, weighs as much as 100 747s, and it's half the size of the Cathedral of Notre Dame. And it's instrumented to measure the precision of particles going through this detector with an incredible precision, for 10,000ths of an inch. And it took a total of 20 years between planning it, starting, and turning on. So, and it's an amazing facility with 1 billion proton-proton collisions occurring every second. It selects about a few hundred interesting events every second and records them for the scientists to analyze. There's about 5,000 scientists total from 180 universities on this experiment. I should also mention the other big detector, CMS, which has the same scientific goals, the same sort of overall strategy, but a different technical solution to every problem. So compact means that it's only 21 meters by 15 by 15 meters, and it's built around a huge magnet. CMS stands for compact muon solenoid because it detects muons, and it's got a solenoid magnet, and similar size collaboration. So these are the basic tools of particle physics, which is, I'm going to say, at least for the purposes of this talk, synonymous with high energy physics. And what we're attempting to doing is answer basic questions. What are the fundamental constituents of nature, and what are the fundamental interactions? And I'm going to use fundamental in the sense of meaning shortest possible distances. It's not meant as a moral judgment on how interesting particle physics is compared to anything else. But it is definitely the field that deals with the shortest possible distances. And because of the uncertainty principle, exploring short distances means high momenta and therefore high energies, hence the need for very large machines. This is the largest experiment ever built, I believe. It took 10 years to construct. It was originally designed to have 14 trillion electron volt energy total, 7 in each beam. And this was 7 times more energetic than the Tevatron, the US previous highest energy collider. In 2008, it had a tremendous accident where some electrical connections failed, and there was a quench which damaged 50 magnets and released 6 tons of liquid helium. And led to some delay and studies, and then run 1 began in 2009 at half the design energy. But run 1 was nonetheless tremendously successful and announced the discovery of the long-sought Higgs boson on Independence Day, July 4th, 2012. So last year, run 2 began at pretty close to the design energy, collected about 1/10 amount of data as all of run 1, and then shut down in December, and it's just now awakening again from the usual winter shutdown. So what the LHC is doing is colliding protons, but what it's doing from the point of view of particle physics is colliding the constituents of the protons, which are quarks and gluons. So we have this sort of schematic picture where you could think of a proton itself as being a beam of quarks and gluons, and these subconstituents, fundamental particles, have hard scattering events which produce anything allowed by symmetries, photons, electrons, muons, also quarks, but the quarks materialize as jets, and also a big mess called the underlying event. So it produces events that look something like this, where there's a bunch of particles that emerge from the collision point and get tracked, and then the computer produces these nice pictures of what the tracks look like. These may not tell you very much about what's going on. And it also shows you where the energy got deposited. This shows the detector sort of unrolled, showing that the energy was mostly deposited in 2 specific places. And then the experimentalists digest these results while the theorists sit around and watch and get at it. Okay, that's the picture. And so far, all these results are described by the standard model of particle physics, which has, you've probably seen this before, 6 leptons, which do not interact strongly, but nonetheless can be produced at the LHC, and 6 quarks, which do interact strongly, and therefore are easy to produce via the strong interactions at the LHC. And they're antiparticles, and they have this funny mass spectrum that we don't understand very well, but we can account for it with parameters. And then forces, so we say, actually the gravity isn't really in the standard model, but we say there are 4 forces: strong, electromagnetic, weak, and gravity. Electromagnetic is familiar, gravity is familiar. Strong and weak have to do with nuclear physics in sort of low energy lives. But the electromagnetic and weak forces are now said to be 2 components of a unified force called the electroweak force. And gravity, we say, is not well described by the kind of field theories we use to describe the other forces. So the electroweak theory, okay, now I'm going into some of the slightly more technical slides, unifies the long-range electromagnetic force with the very short-range weak force. Both of these forces are described by the same kind of theory, which we say is a gauge symmetry. You're familiar with the gauge invariance electromagnetism. There's also a gauge invariance associated with the weak interactions, all part of a larger gauge symmetry. And gauge symmetry famously means the photon is massless and the electromagnetic force is long range, falls off like 1 over r squared. And the gauge quanta are spin 1 particles with 2 polarizations. On the other hand, when we talk about the weak bosons, they are massive particles and spin 1 and therefore have 3 polarizations. So we have to have something else present to provide that 3rd polarization for the weak bosons and complete the unified theory. And that's what we call the Higgs mechanism. So the Higgs mechanism of the standard model, which is going to be part of the focus of this talk, is a theory which starts with the idea when we say all particles are massless to begin with means both in the early universe at high temperature before symmetry breaking. It also just means that the fundamental description in, say, the Lagrangian at short distances. And then we postulate an extra field beyond the ones mentioned so far, the Higgs field, which right now is filling the universe. And it has a potential energy that roughly looks like this. So this is the potential energy in the vertical axis. And in the horizontal axis is the value of the field. And it's not just one field, it's a bunch of fields with a symmetry relating the different components. And so that's represented by a circle, but there's actually two other dimensions as well. And the Higgs field doesn't want to sit up here on top because that costs more energy. As the universe cools, it picks a direction spontaneously and sits down here with a non-zero value. And that non-zero value breaks the symmetry between electricity, electromagnetism, and the weak interactions. It's just an arbitrary breaking. We call it spontaneous. And so, so particles acquire mass then by interacting with this field. The missing polarizations of the W and Z are actually provided by the particles combining with these otherwise would be massless particles to acquire mass. The massless particles being the excitations around this flat direction. And then there's the Higgs boson, which corresponds to excitations which cost energy even when they're long wavelength. So the Higgs field is a classical field filling space, but excitations are quantized, and those quantized excitations are particles called Higgs bosons. So we want to find the Higgs boson to confirm this theory. And the Higgs boson has particular couplings to fermions proportional to their mass, and couplings to the W and Z boson, and also couplings to even massless particles mediated by quantum effects, where virtual particles appear and disappear out of the vacuum, like here's a Higgs turning into a virtual top and anti-top, which can combine into two photons, and similarly to gluons.
Good question.
Yes?
In the previous diagram with this, can't there be more than one mode of the particle inside that funny thing?
So we put in a complex two-component field, so that's 4 directions, which I can't draw. And 3 of those correspond to those symmetrical directions. And then 1 corresponds to the radial direction, that's the Higgs boson. So then, so we say you want to find the Higgs particle. That's not really something you can do with your bare eye because it lives for a very short time, 10 to the minus 25 seconds. It instantaneously turns into a pair of lighter particles as soon as it's produced. And these could be photons, gluons, quarks, leptons, Ws or Zs. And the standard model predicts how many of each type, depending on the mass. And that's partly how we identify that what we found is the Higgs boson and not some other excitation. And of course, when we see any particular event, we don't know that it's a Higgs candidate. The way the discovery is found was by looking for excesses with a particular energy. So this shows a plot of the energy of 2 photons in the Lorentz frame where the total momentum is 0. Call that the invariant mass. And you can see that the numbers of events at any given invariant mass has this smooth function here. Most of those are just due to photons being produced by any number of different processes. But here there's a little excess at a very particular energy, which corresponds to the mass of the Higgs boson. This shows the Atlas experiment, and if you were to just look at Atlas, you'd say, okay, that looks like an excess, and then you get even happier when you see, look, the other experiment, CMS, a completely different experiment, also has an excess, also at the same mass, 125 GeV. And, okay, so you can see it with your bare eye in those plots, but you can also study the statistical significance. So after showing you those pictures, experimentalists digest them and show you what is the so-called p-value associated with any given excess. So the p-value is the probability of observing data that has a fluctuation at least as extreme as what you could observe. If there was no Higgs boson there, and so small is good, means that the excess is significant. And you can see all sorts of little wiggles, but then there's this great whopping dip in the Atlas experiment, and a similar great whopping dip in the CMS experiment. They put a different scale here, but at the same mass, for showing that the probability of that big an excess if there was no Higgs boson is small. And I guess I should say, what you should not say, because reporters sometimes say this, what is the probability of the Higgs boson not being there? That's a much harder question to answer. But the p-value just means this. So that was, good enough to announce a discovery. So that completed the standard model and our understanding of electroweak unification 4 years ago. Extremely exciting, although we've now gotten used to it. We're no longer excited about it, and focusing on puzzles. And okay, so there's this puzzle. Why did Fabiola use Comic Sans when she reported the Higgs discovery? But okay, I'm going to start now on the naturalness part of the story. And I'm going to start that with a quote from Einstein. So, I don't know why Einstein believes this. There's really very little evidence for this principle, what we call it Einstein's principle. But he says this is a property of nature. Nature is constituted so it's not possible to lay down such strong determined laws that within these laws only rationally completely, it is possible, so that only rationally completely determined constants occur, not constants that could be changed without completely destroying the theory. That's what he wanted. So, for instance, this is why he did not like the cosmological constant in general relativity. He did not think a theory was complete if it just allowed you to put a constant in which could take on a random value. And, was this right? Like I said, we don't have any evidence that it was right, but on the other hand, I think we all have a deep, at least I do, a dislike of theories that have adjustable parameters in them and are supposed to describe fundamental physics. We're okay with saying, well, maybe those are just an effective description of what's going on in some particular situation, but we don't like the idea that they're fundamental. So is there a more fundamental theory in which, for instance, you could compute that Higgs potential that I showed a picture of? And we'd be reasonably happy if we could do this, even if that theory involved other parameters, which might in turn be computed in a still more fundamental theory. So part of that computation has to involve, this is probably the most technical thing I can say, has to involve something called renormalization. In quantum field theory, I should say the standard model is a quantum field theory. When you compute quantum effects, you end up computing integrals, integrating over possible virtual particles, which are not well defined. Integrals like this one, for possible directions of the momenta over p squared. So this one is quadratically divergent, or this one which is logarithmically divergent. And so these integrals are sensitive to very large momenta, which come from perhaps very energetic virtual particles or very high mass virtual particles. We say they're sensitive to short distances. And in order to ascribe any meaning to our computations, we have to introduce some way of making these integrals finite. We call that introducing a cutoff. And that's already bothersome. And then we say, well, we don't want our quantum corrections to be sensitive to this arbitrary regulator. So what we do is we say, well, we put in classical effects also sensitive to these arbitrary parameters. And then we define our observable values, which are the sum of the classical and the quantum. And then we call the sum of the classical and quantum, which is defined to be finite, a renormalized parameter. So this is something which has bothered theoretical physicists for a while. I think we've now pretty much come to terms with this. It doesn't mean we can't predict things. It just means we can only predict things in terms of renormalized parameters. But it does mean that the renormalized parameters are adjustable. They can't be determined from any more fundamental principle. So here's the parameters that we're interested in if we want to compute the Higgs potential. So we have this weak scale, which comes from the W and Z masses, which come from the Higgs condensate. So we say the Higgs field has an expectation value. which has a particular value. And you say, well, what is that scale related to? It seems to be very small compared to a scale that we would like to think of as a fundamental scale coming from Newton's constant, or the Planck scale, 10 to the minus 17 times smaller. And what sets this scale is the renormalized value of this term in the Higgs potential. The Higgs potential can be written in terms of two terms, a quartic and a quadratic term. And so this has the feature that you lower the energy by making the Higgs expectation value non-zero, and how big the expectation value is depends on this quadratic term. And then when we want to, if we say we would like to compute it, well, we would put in the quantum corrections. In particular, there's a set of quantum corrections coming from this parameter, which is the coupling to the top quark. And it's proportional to some short distance scale. We don't know what it is squared. And then we have a bare or classical value. So we call this combination the renormalized parameter. And in order to predict this, we would need to have a theory for both this, the bare mass, and this, the cutoff. We don't have a theory for either. So what we would need would be a theory in which the bare mass was determined by some kind of symmetry, like maybe a symmetry that set it to zero, and this cutoff dependence went away. So we had some finite theory, maybe some other. What we actually do when we say we would like a theory in which we could do this computation is say we would like some other particles besides the top that would cancel off this correction. And, okay, so in saying this, we're essentially following a prescription which was laid out in this amazing paper by Ed Tuft back in, I think, 74. And in this paper, he had like 5 different great ideas, but one of them, which I've highlighted here, was this idea of naturalness. So what he said was, if we're going to have arbitrary parameters, and if they're very small, then they should remain small after we compute the quantum corrections, and that would be true if we gain a symmetry when we set them to zero. So he says at any energy scale, the renormalized parameter at that scale can only be small if you could set it to zero and increase the symmetry of the system. So that's the limited sense of naturalness I'm going to be talking about for the rest of this talk. That is, does nature contain arbitrary small parameters, or are they only small because there's some kind of new symmetry? So, and the reason, we would adopt such a principle is that if that were true, there would be some hope of a path towards computing these small dimensional numbers from a more fundamental theory. It would seem implausible if making them small involved some kind of very delicate cancellations. We would say that looked unnatural, just like, if you saw some arrangement like this that seemed to have been placed very delicately, you would say that was probably not just nature alone. And so now, can the LHC address that question? So applying this principle to corrections to the Higgs mass implies that there are particles which can cancel these large corrections due to, especially the top, those are the largest corrections. So that would imply some new particles that would also correct the Higgs mass, but they would cancel this, they would not have UV sensitivity, they would cancel the cutoff dependence. We call these top partners. So essentially all physics of beyond the standard model, which is claimed to be natural, possesses particles we call top partners. And we assume, because they're related by a symmetry to the top, in some cases supersymmetry, in which case we call them top squarks, or in some cases some other symmetry. We assume usually that they're colored, and if they carry color, that means they can be produced by the strong interactions, they can be produced by the gluons inside the proton. They should be made at a large rate by the LHC. So are there any loopholes? Okay, so the main natural loophole I know about. And probably Josh will correct me if there's others. So there's something called neutral naturalness, where you cancel the top contribution to the Higgs via something which is called mirror matter. So the idea is that besides our standard model with our forces, there's a second copy of the standard model, which is just like ours, but with its own forces. And there's a special form to the Higgs potential by a symmetry that interchanges these two models such that the top contributions are canceled by these twin top contributions. And the twin tops don't carry our color, they carry the other color. And so they're hard to study at the LHC. They're not made at a large rate. And that, to me, it seems very clever, but if that's the only loophole, I'll live with it. There's an even worse loophole, which is to say, basically maybe we can't predict everything, or maybe not even anything. Maybe there are just many different possible universes. And we just happen to live in one which has the parameters that allow for observers, and so those universes appear to be fine-tuned and unnatural. And there's no logical reason to be against this principle, but I don't know how to test it either. A more recent idea of a loophole, which is gone by the name of the Relaxation, is maybe the Higgs mass is itself determined by some other field, which they call phi. Okay, so here's the Higgs mass. It has a mass, but it also has a coupling to some other field. And that other field, which they call the Relaxation, actually, has a very weak potential, very weak couplings to anything. And the different values of this phi field correspond to different values of the Higgs mass. They also then couple this Relaxation field to the gluons in this way, which is the same way the QCD axion does, and put in some other potential for it. And what then happens is that if the Higgs expectation value is 0, then you have massless quarks, and the strong interactions don't contribute to its potential. But if the Higgs expectation value is non-zero, the quarks become massive. And when the quarks are massive, you can show that in QCD you get this periodic term in the potential from something called instantons. So the potential for this field, the Relaxation, has the feature that it's got some smooth, straight value, and then it acquires oscillations at exactly the value where the Higgs mass is 0. And so they then say, well, maybe the way the universe evolves is this Relaxation rolls down until the Higgs mass is slightly negative, and then it gets stuck right there, where the Higgs mass is very small. So a clever idea, technically natural in some sense, in the sense of a 't Hooft. No top partners, a very weakly coupled new particle, which could be perhaps the dark matter. It also would give rise perhaps to some parameters oscillating in time, but with a very small amplitude. Other than that, hard to test. Bad news for the LHC. I guess the final loophole I know about goes by the name of Nnaturalness, where N is the number of copies of the standard model. So this is not like the multiverse, because they're assuming that all these N copies of the standard model are right here around us right now. So there are many standard models in our universe. And the only difference between these copies is the value of the Higgs mass. And then they want to argue that only the one with the value of the Higgs mass that's ours ends up getting populated after inflation. So that these other copies of the standard model just don't have a lot of particles in them around. I mean, they're there potentially, but not in reality. Okay, so I can leave it to you to decide which you like better, naturalness or these alternatives. I don't think there's any other possibility. I don't know, does anybody like any of the alternatives better than naturalness? You like the multiverse? Okay. Okay, you've got the multiverse. The others are all logical possibilities, I believe, at this point.
So far.
Yeah, maybe somebody will think of something else. And there's even the twin Higgs version. But okay, instead of sitting around and debating this, we asked the LHC. So the LHC is restarting, Kyle just said, basically stable beams tomorrow. So release the protons and let's see what happens when we go up to, the meat of run 2. I mean, run 2 is supposed to be great. Supposed to go up to total data gathered corresponding to 100 inverse femtobarns, which is like 5 times what run 1 had, and all our cross sections have gotten bigger because the energy is bigger. So this shows the ratio of the constituents of the proton at any given energy between 13 TeV and 8 TeV, and you can see here's 1. So as you go to heavier and heavier particles, those relative luminosities of gluons and quarks become larger and larger, so much more potential for making heavy particles than run 1 did. And in fact, it already began last year with like a 30th of the total data that will eventually be contributed. So, and still in run 1 and in the early part of run 2, I would say no definitive signs of physics beyond the standard model, given the very stringent standards particle physicists have adopted. But, okay, what does this look like? This is from the 2015 data. This is the ATLAS experiment. This is the photon invariant mass. This is the number of events at every invariant mass. Looks a lot like the Higgs, except notice this isn't 125. This is starting at 200 and going up to 1600 GeV. And okay, so here's your expected theoretical curve for the numbers of events. Here it's very bumpy because there's only like 1 event. So statistics are jumpy. And look, there's something. It looks like something. They showed this in December and again at Morion. But look, it's not 125. It looks like the Higgs. It's at 750.
And CMS.
8. Well, let's get to CMS. This is so, and again, we should look at the p-value. So they actually show now their p-values. I mean, now they interpret it in terms of local significance, sigma, but they show it as a function of mass and as width, that is uncertainty in the total energy, which depends on how long it lives. And so you can see there's some excess there, not very significant, and some more significant excess there corresponding. They call it local significance of something like that, 3 or 4. Local significance, of course, just means, what's the significance of something right there. And given that there are many places they could have looked, that doesn't mean that that's the probability of, seeing something anywhere. So you might say, well, what about run 1? What about 8 TeV? So they recently showed what happens when you look at 8 TeV in the same channel. So this shows if they optimize cuts looking for a spin 2 particle versus a spin 0 particle. And you don't really see anything but, an upward fluctuation at least. But again, the ratio of cross sections at 13 is to 8. Could be, 4 or 5 or 6, depending on what's going on. Okay, and what about CMS? Depending on which category of events you look at, they've shown different plots. I don't think you would look at this, I wouldn't look at this and say, wow, but there is, an upward fluctuation in the same place. And they now have shown at Morion a combination of categories of events at both 13 and 8. This is the famous p-value, so small is good. So you can see small fluctuation here, which is not in the same place, but not big, and then a bigger fluctuation here in the same place as Atlas. So what do you make of that? I'm calling it gamma gamma, GaGa for short. And that also has been something describing the reaction of the theorists, given that there are 250 papers so far. I think it's obviously too soon to say, but given that the Run 2 is turning back on tomorrow and they may double the data set this summer and by December have a lot more, we'll know whether the significance is increasing or decreasing. And here's one of the papers on that topic, and this is actually kind of a meta paper where they attempt to fit the number of papers on this topic as a function of time, and they come up with a theory for that. They compare that with other similar events in the past. Most of these past things went away. That is, they were indeed statistical fluctuations. So he predicts 310 papers by June 1st. So there's another prediction. Okay, so I'm writing one of those. Devin Walker. And based on a model that I happen to like anyway, which is a theory in which our Higgs boson is a composite particle, much like, say, the pions and kaons of QCD, only, of course, a much stronger force, a much higher scale. And so a composite particles typically don't just come in small numbers. If you look at the particle data book for the pions and kaons, you find they're part of a whole family of particles. Composite particles, constituents can be combined in different ways. And we even had written down a theory of a composite Higgs a while ago, which just happened to have one extra pseudoscalar in it. So we just said, okay, well, what if we put that extra guy at 750 GeV? So is that the natural place for it? So our theory has some parameters in it, and sort of random values of the parameters don't put it heavier than the Higgs, but 5 times heavier than the Higgs. I'll say 5 is order 1. And then our theory also has top partners in it. It needs to have top partners in it in order to cancel the top generated sensitivity to short distance scale. So we can use those to generate both coupling to the gluons via diagrams like this. So this is our new scalar. We have these so-called triangles where we have these new particles, top partners and also bottom partners in the loop, coupling to gluons, also photons. Because these particles are both charged and colored. Okay, so then does that work? So in principle, we could go and simulate events in this theory. For now, let me actually just cheat and use the fact that this CERN collaboration with a lot of people did a lot of work, paper that came out pretty soon after those excesses were announced, saying what is this GaGa resonance at 750, and they provided some sort of useful benchmarks. They said, well, if we look at the width of this particle to gluons and the width to photons, you can compute in terms of the width to gluons what the production rate is, if it's produced by gluon-gluon fusion. And then you can compute the number of photon events by the decays. And then, depending on how broad it is, you could live anywhere in this region in terms of those two parameters. If it mainly is produced by gluons and decaying to photons, then you should live in that blue region. And if the width to gluons was too big, you would produce too many events where gluons produce this particle and then it decayed to two gluons, which would look like two jets, and that would exclude it. So you want to live kind of in that little banana, or anywhere in this region. So, okay, so if I put that in, and I put the top partners, if I put the compositeness scale for this the Higgs boson about as low as it's allowed to be by data, 500 GeV or so, and put the top partners at a value which gives a good value for those couplings to gluons and photons. And I put in a second set of top partners that are required by the theory, but they're actually heavy enough they don't do much. So the largest, the sensitivity is basically determined by the masses of the lightest top partners in the compositeness scale. So if I fix the compositeness scale to about 500 GeV, the partners should be at about 1.4 TeV. And we then find that the width to gluons and the width to photons are given by these numbers. The total rate for going to 2 photons is about 10 to the minus 6 times the mass, and the total rate for going to 2 gluons is about 10 to the minus 3 times the mass, which puts you right here, sort of right on the edge of being excluded but not excluded. So I found that pretty heartening. These are nice values for this model. The theory tries to work, I would say. Composite Higgs theories try to explain this. Okay, so I'm going to conclude now. I'd say run 2 was off to an interesting start. So you could give us a clue to naturalness, should find top partner, should find new stuff at around a TeV or not, which might be a clue that one of those other alternatives to naturalness is better. So the theorists are pretty excited. I'd say, remember previously I referred to us as vultures. The hyenas, they're experimentalists, they're still being cool, but we'll see if that lasts through the summer. All right, thanks.
Matt?
So in the first part of your talk, I think if I understood you right, you said that normalization means that the Kelvin constants can't be unique. Right, as opposed to Einstein's open. Is that what you meant?
Yeah, so once you renormalize, you're saying, well, I'm just going to say I'm ignorant about the cutoff physics.
Right.
And I'm just going to put in a renormalized parameter and I can adjust it.
So you could have some more fundamental theory that's not perturbed.
Right, it could be that there's a fundamental theory that predicts the parameter. And then I should just compute it.
Right.
But then I wouldn't have to renormalize. That fundamental theory should give me finite corrections. And I should just be able to compute it.
Okay. But
Yeah.
I mean, the fact that there's renormalization in the standard model certainly doesn't mean that there isn't a theory with unique.
Right, so if I just stick within the standard model,
Yeah.
then I can't compute the parameters of the standard model.
Right.
I need a theory which removes the cutoff sensitivity of the renormalization contributions to those parameters.
So I have a two-part question. One is, what would be the interesting things one would learn if one were to collide the Higgs bosons?
That would be wonderful.
From a theory point of view, and then secondly, if you knew kind of what the status is for the LHC, what would be required? And again, so I'm not I'm not.
We can't actually collide Higgs bosons, right? Because they live 10 to the minus 25
Yes, that was
seconds.
my question.
But as virtual particles, there is di-Higgs production, which is sensitive to the Higgs self-coupling. Right? So if you produce a Higgs as a virtual particle and it decays to 2 Higgs, so in a virtual sense, you can probe the properties of what happens when Higgs bosons connect with each other. I think di-Higgs, which we're not going to probe anytime soon probably, but you know, ambitious future programs for high energy physics would probe the rate of Higgs production. Is that your question?
Well, I mean, again, I'm not a particle physicist, so I was just wondering if
Yeah.
there's in general terms, what would we be able to learn?
Well, we would love to know what the Higgs coupling to itself is. The standard model predicts that. Various theories beyond the standard model may modify that. And that could be probed by virtual effects.
Andy?
So what if we just find the new gamma resonance and then nothing else? What do we learn?
So that would be kind of puzzling because it's a neutral particle and it decays to photon. So if there are virtual particles that produce that coupling, if there are any of the standard model particles we know, like top or W, charged particles, it should also decay very rapidly into those particles, which means it would just do that and they wouldn't see the photons. So whatever is produced, the virtual particles that produce that should be heavier than half its mass. And I think that would be quite puzzling to only see the new particle and not see any other signs of charged or colored particles. At least charged. We don't actually know what the coupling of gluons is, but the theory seems to work a bit better for couples of gluons. Okay, I would guess that that won't happen.
We got two unnatural particles at least.
Well, okay, so one is just unnatural, and the other one is not only unnatural, but sort of inconsistent with sensible quantum field theories. That would be worse.
Any other questions? Yes.
Well, the data released this summer be large enough such that we not only know whether this exists or not, but we also know the angular dependence, like whether it's spin 0 or spin 2.
I think it's not inconceivable. Right? There's already, maybe, it's not inconceivable. I don't know.
So now we don't know about, we're not sure about this.
Yeah, spin 2 is also interesting, of course, maybe even more.
Yeah, I think by the end of the year, we would have enough for some sort of preliminary rank. Within the summer, it's a little hard to say, but by the end of the year,
Yeah.
if it's real.
I mean, you can not only tell if it's real, but indicate whether spin 0 or spin 2 is preferred by the end of the summer.
Yeah, by the end of the summer, I think it's tough, but end of the year, I think it would.
Yeah.
Maybe we'll see it decaying into new things to see photons. Any other questions for Anne? Let's thank her again.